Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Bridging Between Algebra and Calculus series and concerns basics of logarithms. This guide describes logarithms and their basic properties. It identifies the link between logarithms and exponential functions. It shows how to solve exponential equations using logarithms. Introduction. Before the invention of the calculator, methods for shortening the processes of multiplication and division were important in mathematics. In 1593, two Danish mathematicians used trigonometric tables to reduce multiplication and division to the level of the easier skills of addition and subtraction. This method inspired the mathematicians John Napier and Jobst Burgi to independently develop tables based on indices which performed a similar purpose. Napier named these numbers logarithms. This study guide will help you understand the link between logarithms and exponents. It will also show you how to switch between the logarithmic and exponential forms of a particular piece of mathematics. This study guide assumes a good knowledge of the properties of exponents. The study guide Laws of Indices can help you with this. Logarithms exploit the laws of indices to transform multiplication into addition and division into subtraction. Logarithms and exponents are closely linked. Just as subtraction is the inverse operation of addition and division is the inverse operation of multiplication, logarithms are the inverse operation of exponentiation, which is raising a number to a power. Because of this, you can use logarithms to help you solve exponential equations. See later in this guide. Exponential equations. One of the most important uses of logarithms are as a tool to solve exponential equations. An exponential equation is one where the unknown is part of an exponent within the equation. For example, 10 to the power x equals 100. The unknown x is part of the power of 10. 4 to the power 2x equals 9. The unknown x is part of the power of 4. 6 to the power 1 minus x equals 6.2. The unknown x is part of the power 6. All the above are exponential equations, as the unknown x is part of the exponent. Exponential equations can be very easy or very difficult to solve, and there tends to be no in between. A slight change in an equation which is easy can make it very difficult to solve. Example. Solve 10 to the power x equals 100. This is an example of an exponential equation as the unknown x is part of the exponent. Remember that 10 squared equals 100 and so the solution is x equals 2. This type of exponential equation is easy to solve. However, it is common to give the answer x equals 10 as 10 times 10 equals 100. It is important to remember that you are dealing with indices here, not multiplication. A very minor change to this example can make its solution very difficult. Example. Solve 10 to the power x equals 101. Solving this by hand is very difficult, but you can use logarithms to help. Using logarithms to solve simple exponential equations. You can write a general exponential equation as y equals a to the power x, where, in the previous example, y equals 101, a equals 10, called the base of the equation, and the exponent is x equals x. In mathematics, there is an equivalent way of writing this general exponential equation in terms of a logarithm. This is x equals logarithm to the base a of y. Here you have the exponent x is equal to a logarithm, which is written as log. The subscript indicates that the logarithm has a base of a and you are taking the logarithm of y. There is no multiplication here, as taking a logarithm is a different operation in mathematics. You would pronounce the notation this as log to the base a of y. The base of a logarithm can be any positive number, but never negative. You can move freely between the two types of equations using the logarithmic transformation. Y equals a to the power x can be transformed into log to the base a of y equals x, and vice versa. If you have an exponential equation, expressing it in logarithmic form has an advantage, as log to the base a of y can usually be found using a calculator. Before you attempt to solve 10 to the power x equals 101, you should make sure that you understand how to switch between the exponential and logarithmic forms of equations. Example: convert the exponential equation 10 to the power x equals 100 to logarithmic form. In the exponential equation 10 to the power x equals 100, the base a equals 10, the exponent x equals x, and y equals 100, so you can use the logarithmic transformation. The equation 100 equals 10 to the power x can be transformed to log to the base 10 of 100 equals x. You know from the first example in this guide that x equals 2, and so you can write that log to the base 10 of 100 equals 2. You can think of the mathematics log to the base 10 of 100 asking the question, what power do you have to raise 10 to get 100? And the answer is 2. Similarly, the expression log to the base 7 of 49 asks the question, what power do you have to raise 7 to get 49? And the answer is also 2. Example: solve 10 to the power x equals 101. Now let's return to the example from before, but now you can use the logarithmic transformation with a equals 10, x equals x, and y equals 101. So the equation 101 equals 10 to the power x can be transformed to the logarithmic equation log to the base 10 of 101 equals x. You should notice that the left hand side of log to the base 10 of 101 equals x is just a number. This number is not obvious though, as it is the power that you need to raise 10 to get 101. You can, and should, use a calculator to find it. Calculators calculate logarithms in various ways, and you should consult the instruction manual of your calculator to help you work out how to do it. You should get x equals 2.004 to 3 decimal places. To check the answer, use your calculator again to find that 10 to the power 2.004 is about 101. The answer is only approximate as you have rounded the 2.004. Example: solve 1 over 25 equals 6 to the power x. Even though this example involves working with fractions, the logarithmic transformation works in exactly the same way. Here, the base a equals 6, the exponent x equals x, and y equals 1 over 25. So, the exponential equation 1 over 25 equals 6 to the power x can be transformed to log to the base 6 of 1 over 25 equals x. And you can use your calculator to see that x equals log to the base 6 of 1 over 25 equals minus 1.796 to 3 decimal places. Solving more complicated equations with logarithms. Many exponential equations contain complicated exponents. You can solve these equations using the logarithmic transformation in exactly the same way as in the previous section. Example: solve 8 to the power 3x minus 2 equals 24. Here, it is not easy to find what x has to be to satisfy the equation. However, expressing the exponential equation as its logarithmic form is useful. So, using a base of 8 and an exponent of 3x minus 2, the logarithmic transformation gives 8 to the power 3x minus 2 equals 24 transforms to log to the base 8 of 24 equals 3x minus 2. You can solve log to the base 8 of 24 equals 3x minus 2 for x by conventional rearranging. See the study guide, Rearranging Equations. You need to subtract 2 from each side and then divide each side by 3. This gives x equals 1/3 of log to the base 8 of 24 plus 2, which may look complicated, but it's just a number. Careful inputting into a calculator gives x equals 1.176 to 3 decimal places. To check, put this result back into the original question to find that 8 to the power 3 multiplied by 1.176 minus 2 is approximately equal to 24. You should notice the use of brackets to help you in the above calculations. Brackets are very useful when dealing with logarithms. For example, log to the base 8 of 24 plus 2 and log to the base 8 of 24 plus 2 are not equivalent. Properties of logarithmic functions. You can use specific values of a and x along with their connection to exponents to find special properties of the logarithmic function. Property 1. The logarithm of 1 is 0 regardless of the base. From the laws of indices, you know that a to the power 0 equals 1. In other words, raising any number to the power 0 gives 1. For example, 4 to the power 0 equals 1, 100 to the power 0 equals 1, and so on. You can use this in the logarithmic transformation to give a to the power 0 equals 1 transforms to log to the base a of 1 equals 0, which reveals that the logarithmic equivalent of the exponential equation a to the power 0 equals 1 is log to the base a of 1 equals 0. In other words, regardless of the base, the logarithm of 1 is 0. Example, what is log to the base 14 of 1? As the logarithm of 1 is 0 regardless of base, log to the base 14 of 1 equals 0. Property 2. The logarithm to base a of a is 1. From the laws of indices, you know that a to the power 1 equals a. In other words, raising any number to the power of 1 gives that number. For example, 4 to the power 1 is 4, 100 to the power 1 is 100, and so on. You can use this in the logarithmic transformation to give a to the power 1 equals a transforms to log to the base a of a equals 1, which reveals that the logarithmic equivalent of the exponential equation a to the power 1 equals a is log to the base a of a equals 1. In other words, the logarithm to base a of a is 1. Example, what is log to the base 8 of 8? Using log to the base a of a equals 1 with a equals 8 gives log to the base 8 of 8 equals 1. Important bases for logarithms. The two most common bases for logarithms are 10 and e, where e is Napier's constant, e equals 2.71828, and so on. Firstly, logarithms with the base 10 are called common logarithms and are commonly used to manipulate scales which go from the very small to the very large. On your calculator, the common logarithm is usually denoted by the log button. Logarithms with a base of e are called natural logarithms. The number e is one of the most important numbers in mathematics and is related to compound interest calculations, amongst many other things. Exponential equations with e as a base describe exponential growth, such as populations, and decay, such as the decay of radioactive isotopes in the sciences. The natural logarithm offers a way to manipulate exponential equations with a base of e. It is common in science to see natural logarithms used to change the curve of an exponential equation to a straight line, which helps in an analysis. Natural logarithms also play a crucial role in mathematics, as they are the only logarithms which evolve out of calculus. On your calculator, the natural logarithm is usually accessed via the LN button. Changing the base of a logarithm. The numbers 10 and e are not the only bases for logarithms. In fact, any positive number can serve as a base for a logarithmic function. Most modern calculators can create logarithms of any base, however some do not. You shouldn't worry, as logarithms are flexible and you can change a logarithm from any base to either base 10 or base e. You can then use your calculator to perform the calculation in the accessible base. In general, if you want to change the base of a logarithm from a to b, you use log to the base a of x equals log to the base b of x divided by log to the base b of a. The logarithm of a number x for base a is equivalent to the logarithm of the same number x in base b divided by the logarithm of its original base a, also in base b. Now, by replacing the case b with the common logarithm base 10 or the natural logarithm base e, you can use your calculator to obtain the value of log to the base a of x. To change from base a to base 10, log to the base a of x equals log to the base 10 of x divided by log to the base 10 of a. To change from base a to base e, log to the base a of x equals the natural logarithm of x divided by the natural logarithm of a. Importantly, you can use either of these equations and you will always get the same answer. Example: find the value of log to the base 3 of 7. Firstly, let's change to base 10. Log to the base 3 of 7 equals log to the base 10 of 7 divided by log to the base 10 of 3. Put these in your calculator. Equals 0.845 divided by 0.477, which equals 1.771 to 3 decimal places. Now let's use natural logarithms. Log to the base 3 of 7 equals the natural logarithm of 7 divided by the natural logarithm of 3, which equals 1.946 divided by 1.099 from your calculator, which equals 1.771 to 3 decimal places. Check the answer by finding that 3 to the power 1.771 is approximately equal to 7. Further guidance and information. If you have any further questions about logarithms or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor, or make an appointment to see a Learning Enhancement Tutor in the Dean of Students office. Telephone 01603 592761. Email dos.help@uea.ac.uk, or visit our website www.uea.ac.uk/dos/let. There are further resources on many other aspects of numeracy, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.